I have a different background for myself. Just prepared, opened up the lecture on deep learning. Looking at the place where we could start. Okay, gotcha. Okay, regularization, vector regularization.
This is start to university on your background.
Yeah, so this is the Delta building. This is the building where I work. This is the Institute of Computer Science, Mathematics, and Statistics. This is where I spent time when there is no quarantine and COVID and that kind of stuff. This is the place where I work.
And studying in English, or it's different?
Yeah. I teach. I teach in English. I teach English. Well, I don't teach English. I teach in English. I don't know Estonian as well as to teach people in Estonian. I can pretend to know Estonian, but I am definitely far from real speaker of Estonian. My wife is much better. She studied it for some time, and I quit at some point when there was too much work. I couldn't really keep up. Alexander, are you speaking French?
Oui.
Not
well. I have taken it for one semester here at the university in Canada, but as I'm not using it, so I forgot everything.
Okay, but Toronto is not that French-speaking, right? The Montreal is more French-speaking place.
Yeah. Quebec is a French-speaking province. Not only Quebec, but people mostly know about Quebec.
Okay. Lena, what about you? Est-ce que tu parles français?
Mówię po polsku.
Gotcha. This is great. And this is excellent. Thank you very much. All right. Let's get back. So we just discussed that in order to use L2 and L1 regularizations for deep learning, you need to add when you do backpropagation, you need to add terms, right? For L2 term, you need to add lambda times W5, or depending on which weight you do the backpropagation, you need to add lambda times that weight. And for the L1 backpropagation, it's even simpler. You just need to add lambda. And obviously, if you don't know what backpropagation is and how does it work, then it might say very little to you. But hopefully we could catch up a little bit in the end of the class and review the backpropagation, so you could come back to these slides and it would start to make more sense. Yeah, for now, let's move on to so yeah, here I just wanted to make a small comment that I haven't seen people using L1 for deep learning too much. I have mostly seen people using L2 term, and this is what usually is called weight decay for deep neural networks. Another way to do regularization on deep learning is called dropout, right? So as the weight decay is not the only way to do regularization in deep learning. The other one is called dropout. Okay, so if you have read about dropout, so I guess this it makes sense to since we have two people that are affiliated with University of Toronto, it makes sense to say that the dropout has been discovered, has been explored, has been published by University of Toronto. And the paper you can find here, I actually personally think it's one of the most influential papers in machine learning for many, many years. I do suggest reading it. I think it will definitely help you understand many of the things that we have been discussing in this lecture and the other lectures. A dropout is extremely simple. Extremely simple. It's one of these kind of ideas that when you understand it, when you know about it, when you hear about it, you're like, oh, this is so beautiful and so simple. Why didn't I come up with this beautiful idea? So what dropout does is you take a point from your training data. Here is your point. And for each of these points, you kind of do a feed-forward pass as you normally do. But then when it comes to neurons, these circles here in the network, they're called neurons. And when it comes to neurons, you flip a coin, right? You do a coin flip, toss a coin to my Witcher, and you basically choose whether you drop the neuron or you leave the neuron with the probability of P. Right, so there's some probability of silencing the neuron, let it be heads, and there is another probability, 1 minus this probability of keeping the neuron in the network, which is 1 minus P, right? So, so here we don't really need to have P equal to 0.5. It's not a real coin that we are tossing. It could be any P. It could be a very small P. It could be a very large P. It doesn't really matter. In real life circumstances, this P is usually about 0.5, about 0.3, depends on the network. Sometimes people use 0.5, and I think it's quite often that the people use 0.5, but it doesn't have to be like this. So for each of the points, you toss a coin, and for each of the points of the data set, and for each neuron in your neural network, which is 4, in this circumstances, we have just 4 neurons. For each one of them, we toss a coin, and with probability P, in this case, it's 0.25. Let's just take it for this example. We drop the neuron, okay? With the probability of...
Does that have anything to do with the fact that there's 4 neurons? You picked 1/4 because there's 4, or no, nothing?
Yes, it's my piano in the bushes just to make the example work. Exactly. Yeah, so the probability is 0.25 is just because there are 4 neurons. I didn't want to drop too many neurons. I didn't want to look too suspicious. Why didn't I drop more neurons? Because if the probability would be 0.5, I would need to drop more neurons. So we toss a coin for the first neuron. It's heads, and we need to drop the neuron, switching off the neuron completely. So what does it actually mean, switching off or dropping off the neuron, right? Okay, didn't really say that here. I just keep tossing and saying that this one, we keep this one, we keep the other 2, and so on and so forth. But here I come back to this question. I'm asking, what does it actually mean to switch off the neuron? It just means that it takes the same inputs as usual. So in this case, it's W1 and W3 multiplied by the inputs, but then it propagates onwards just 0, right? So whatever it outputs is 0. Doesn't really output any other signal besides 0. And we mark this with a cross. With a red cross, it means that the neuron has been dropped. And that in those circumstances, all the signal that go through the network just go through the second neuron right here. It becomes the bottleneck of the network. In principle, all the, well, it's not neutrons. I think this was the default spell checking. It's a neurons. It's not neutrons. I need to check. I need to correct this. Neutrons. All the neurons can be dropped. So we can drop all the neurons. But normally it doesn't happen because of the probability of this happening is very, very, very small. What would happen? But given that this happened, just let's imagine this happened. What would happen to the class scores? What would we predict? We would just predict 0. Yeah, exactly. We would just predict 0. So nothing really bad happened. It's just we would predict 0, which would be probably not correct, but still would be kind of fine. We would be able to carry on. This scenario is super unlikely unless you have like this small network like what we have, like just 4 neurons. For every point, you do this this coin flipping differently, right? So you drop different neurons with each point. For each point, you get different neurons dropped and different neurons kept. For example, this would be the first neural network for one point. And if we take another point, this could be the second neural network, okay? These are the possibilities. So for each of the points, we may end up using completely different neural networks. And this has been shown to be a very nice regularization strategy because we cannot really depend on any of the neurons that we have trained in the neural network. So the neural network should be generalizable enough to operate on any random subsample of neurons, right? So the neural network should be able to operate correctly with any random subsample. And that's what makes this idea so beautiful and so elegant. It's just for every point in your training data, you drop random number of neurons, and that seems to help to train more generalizable networks, which is in fact what happens in the brain. Many of our neurons do not respond to the inputs from our neurons. It just gets lost, the current gets lost, and not all the neurons fire in response to other neuron inputs. And this is what tries to emulate the situation when you just have some of the neurons taking nap at random points of time, not firing, and it seems to help to produce better performance. Yeah, that's pretty much it. Yeah, we don't change the weights, so these weights are the same. It's just the signal is 0. Just to compare, how does L2 and L1 regularization compare to dropout? L2 regularization forces all weights to be close to 0. L1 regularization forces some of them to complete 0 and some of them to close to 0, while dropout forces random weights to 0. Okay, so this is the difference. L2 regularization forces weights to be close. L1 forces some of them to be complete 0, and the dropout forces random weights to be 0. Yeah, so despite some differences, these methods belong to so-called explicit regularization methods, which is basically explicitly limiting the predictive power of the model by introducing additional constraints. So in both cases, we introduce additional constraints. In the case of L2 regularization, we force the model to use very small weights. In terms of L1 regularization, we force the model to use fewer weights and smaller weights. And in terms of dropout, we force the model to be as generalizable as possible by just randomly knocking out some of the neurons of the model. Okay, any questions here? So this is just to wrap up what we had. So this is basically what I meant by this picture. When you explicitly limit predictive power, your model is too powerful. So you just make the life of the model a little bit harder to make it stronger and more useful for the real life applications. Okay, that's the idea. Any questions here?
When it was discovered, because as for me now it looks like very obvious, yeah.
Yeah, it's that's what the beauty of the I mean evolution has been discovered in, let me know, right? It's a couple of centuries ago, but the idea is so beautiful and so simple. So yeah, so it actually been discovered, I think it was like 2000s, so it was 21st century when it was discovered, not so long time ago. But it's a beautiful paper. You should definitely read it. It also has a lot of mathematical proofs about why it doesn't work and all that kind of things. Well, in fact, I wanted to go back to my collaboratory. Just to, okay, I ran out of my runtime. So if you guys also ran out of runtime, that's okay. You just have to run this first cell in we shall use CIFAR10 dataset. So that's saying that we will use a data set of small pictures. Now it will be loading the CIFAR10 data set to my virtual machine. I get 25,000 images, 32 by 32 by 3. Simeon, what do you think? Why the hell we have 25,000 32 by 32 by 3? What is this 3? Let's start with what is 32 by 32?
Pixel shape.
Size of the picture.
Pixel shape. What is 3?
I don't remember.
Color.
Color. It's RGB. R, G, and B. Okay, that's why it's 3.
Ah, okay.
What is this? Oleg, what do you think? What is this? 25,000 times 1. Any ideas?
Number of pictures. This 25,000.
Yeah, and what do you think? What do we have in this train labels shape? Train labels. What do we contain there? What is in there?
Labels.
So classes for each picture, right? So what are the classes for each picture? Let's run this function plot curves. I will explain what the hell it does a bit later. And if you run this cell with a lot of visualization code, you will see examples. So remember, we had it yesterday, the MNIST data set. We had this visualization function which visualizes the examples of each digit. Now you can see what are the examples of each class in this CIFAR10 data set. You look at the, for example, cats. These are cats pictures, 32 by 32 by 3. So these are colorful pictures, 32 pixels by 32 pixels. You have horses, you have sheep, you have trucks, and so on and so forth. So this is the CIFAR10 data set. It has 25,000 images like that. I think it also has 10,000 test images like that, okay? So we are going to use that one. Here we normalize the data. Why do we normalize data? Olena, what do you think? Why do we normalize the data? And yeah.
I don't remember.
Igor, why do we normalize the data? You're muted.
No, just to get like, just to get, I think, 2 points for R, G, and B. Not too many points, just to get 2 of them and to work with 2 of them. I don't know.
Kenneth, what do you think? Why do we normalize the data?
Just to not overcount the fact that color has a high number, 256, whatever. Same range as for everything.
Yeah, so we just try to make sure that everything is centered around 0. And also it has a standard deviation. So we divide by standard deviation. So the standard deviation would be, we basically put every image into the same range, okay? We make sure that all the images are in the same range. So we wouldn't be judging the pictures based on their background, because the background may be too important and may shift the image in the distribution. So we try to make sure that all the images are centered around 0, and there is the same range of the pictures, right? So we just try to make sure that all the pictures are having the same range, and that is just to make sure that the prevalent color, for example, does not make us decide on the class. For example, we wouldn't be deciding on a class of that horse here just because it had the blue background. We wouldn't think that this is a sheep, right? Something like that.
If I may, the simple approach is just to divide by 255, correct? But this approach does not take into account this possible difference.
Yeah. So 255 is when you know that your pixels are of intensity from 0 to 255, which not always be correct. Sometimes it could be 16-bit images. But in this case, we actually subtract the mean of all the images. So we make sure that the center of all the images of all the distribution is 0.
Yeah, you make it.
We try to normalize. We try to make it for the normal distribution. Yeah, that's basically the reason why we normalize it. And in fact, I will tell you that without normalization, the neural network would still work. but with normalization, it works slightly better. That's the whole thing. It makes it easier for the neural network to compare images if you normalize them around 0.
So, but so other approaches where you have the color values between 0 and 1 instead of normalizing them around the middle, isn't that preferable? Because like white has 255 as a value for all three RGB. So like, so some colors have higher weights just because of how they're coded in RGB, you know?
When you have RGBs, then basically each of these matrices, for example, R or G or B, whatever, the 255 is the highest intensity of this specific color. It's not white in that sense. So you need to get white when you have all the colors 255.
Yeah, well, I know that. Yeah, but some colors just have higher values. So
this is basically what we are trying to achieve. We're trying to make sure that all the colors are centered and having the same range. So there is no that kind of dominance by one color. There is no dominant blue, or there is no dominant red or something like that. So we're trying to make sure that everything is having the same ranges, and then we could and then it would be easier for us to compare between, let's say, frogs and cats. So we wouldn't really pay so much attention to the background.
Yeah, in our in our computer vision course, we did the same step, but we always put it between 0 and 1.
It's fine.
I'm curious about the difference
between 0 and 1.
Yeah.
I guess for the neural network, in that case, it's better if you have the normal distribution, or something that looks like a normal distribution. But I think it both would work. So I don't really have a good intuition. Why would you do one and you wouldn't do the other one? Sometimes I do normalize from 0 to 1. Sometimes you're happy to normalize by mean and standard deviation. Sometimes I actually use raw images as they are. It really depends on your domain. I think in this case, we try to do the normalization just as a matter of selecting the best processing pipeline to get our network perform slightly better. I just experimentally saw that if you use this normalization, it works slightly better.
Yep, sure. Just curious.
No, it's a very good question. Here I define my model. It's a very simple model. It has, I think you have seen this Keras blocks, right? So you have a sequential model. Then you have convolutional layer, you have an activation function, you have batch normalization. I wonder why it's LO, not RLO. Huh, weird. I just wonder why there's no, it's a bit weird. I must have made a mistake. Can you guys just make it ReLU? I'm not sure why it was the other one. It should be rectified linear unit, so it should be ReLU. I guess it would make sense if you guys change it to ReLU, to add R in the beginning. This is a strange blinder from my side. I haven't seen that previously in my code. Yeah, so we have a couple of blocks. You can see that we have activation function, batch normalization. It doesn't really matter. We have dropout, which is important. We have a dropout here. And what we have studied so far, we have this kernel regularizer. And we have a function in Keras called regularizers.L2, which is a L2 regularization. So it doesn't really have a name weight decay. It has regularizers.L2. And here we say lump, as we used to say for the linear regressions, okay? So that's the strength of our regularization. And you can see that this kernel regularization is only applied to convolutional network, convolutional layers, not to activation, not to batch. Batch norm, because batch norm and activations, they are part of the convolutional layer. So these are all part of one layer. They are not separate neurons or something like this. They are just part of the same layer. We also have a dropout with 0.2, which means that we drop 20% of this convolutional layer neurons. Actually, this is not really of the convolutional layer neurons, but rather of the max pool version of this convolutional layer neurons. We repeat the same structure here, the same block. It's just here we have 0.3. And here we repeat the same structure, and here we have 0.4. We also increase the number of filters in the convolutional layer. I think it's one of the standard neural networks that you can find up there. Something of kind of ResNet type of architectures that you repeat this kind of blocks all over again. I think in ResNet you have a lot more of these blocks, but I think for our case, it doesn't really matter so much. Do you have questions about the architecture? You probably have seen this kind of architectures before.
Yep.
Yeah. What is a ResNet? I didn't get.
ResNet is it's a very standard neural network that people use up there in the machine learning community for classification problems. It has a lot more layers, and it has a very standard structure. It has this convolutional network followed by activation by batch norm, and then again convolution by activation by batch norm, and then max pooling and that kind of stuff. So that basically it's a network that has a lot more of these blocks, and the structure of this network is fixed. So you know exactly what is the structure of this network, because each one of these networks has a special name. So if you combine enough of these blocks, you will get this ResNet 101. It has 101 layer and has a very fixed structure. So the people call it ResNet 101, for example.
Okay, so this is a kind of template.
Template, yeah, it's a template. It's a template for the model, exactly. So here we initialize this model. Basically we define the function called define model. And in here, we initialize the model with lambda equal to 0. So no regularization. No regularization is happening here. We compile this model with sparse categorical cross-entropy. It's a almost binary cross-entropy, but just for more than one class. Remember that we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes. So we can't use binary cross-entropy because binary cross-entropy is meant for binary classification. For multi-class classification, we use something that sounds complicated called categorical cross-entropy. And in this very case, I use a very special species of the categorical cross-entropy, which is called sparse categorical cross-entropy. It's just one of the fancy ways of saying that you can just give me a vector of classes and I'll be happy with that. Okay, that's just a fancy way of saying give me a vector of classes. No need to do one-hot encoding. Then I use Adam, the optimizer, with a learning rate of like that. And I look for accuracy, that's all. So I just initialize my model. I also print out the summary of the model. So let's take a look at the summary. Here is the summary of the model. I have 309,000 weights of the model. So actually trainable out of them trainable are 308,000 trainable weights, which I can actually train. And this is what I do. This is what I do here. I train the model. I use my normalized data. This is the normalized data. I use my vector of classes. I use batch size of 64, which means that every time I run through the network 64 images, and I do 20 iterations, and 20% of my data I will use as a validation set. Okay? Make sense?
Yep.
And then I run it. Yeah, also take a look, pay attention. I'm actually storing the history of my training in a variable called history. And we will need this variable. So remember that I have, I initialized this function called plot curves, and that uses a history object as an input. So what this history object contains is it contains actually the losses or errors on each iteration. And it also contains, so this, when I say loss, it means the error. When I say just error, it means train error. If I say val loss, it means validation error. So this one will plot two curves. One of them is training error and the other one is validation error per epoch. Do you guys know what epoch is? Simon, what epoch is?
Epoch, I understood that this is when we train our model, every epoch starts, finishes, every epoch ends with the backpropagation.
No, not really. Not really. But we're kind of getting there. Anybody else? Igor, do you know what epoch is?
It's a variable in a function, but actually, I think this is like a cycle of feeding of this neural network. So we are trying to fit the model cycle by cycle, improving the accuracy of the model. So I think epoch is just one cycle of the feeding.
Training.
Yeah.
Yeah. So you feed in training data into your model by batches. Kenneth, what was the batch size that we chosen here?
64. So
64.
Yeah. So 64 things go in, and then we do that 20 times. 20 epochs.
So there is an important caveat here. It's not that we just put 64 images 20 times, but
no,
it's
64 at a time.
At a time, but one epoch means that we take 64 images. Oleg, what was the total number of training images?
25,000.
25,000. 25,000. So my question to you guys, what if I divide 25,000 times 64? What is this number? I mean, I'm not asking you about specific number. What this number tells me. Olena, what this number will tell me if I divide 25,000 by 64? Kenneth.
The number of
steps
of batches you have to do.
Exactly. This is the number of batches that I need to do in one. What is this? In one epoch. So this is one epoch. So one epoch it's basically the cycle in which I go through entire training data using my batch. So I take a batch of 64, I take a second batch of 64, I take a third batch of 64, and I go through entire training data. So when I finished, I went through the entire training data. This is called epoch. And I do 20 epochs, meaning that I do 20 times the circle around all my training data. Does it make sense, ladies and gentlemen?
Yep.
Okay.
And every
Hold on. Not too fast. Okay, go ahead. Ask.
Yeah, go ahead.
You got it. Okay. Oleg?
What I wanted to ask regarding these epochs.
So you take a batch and you go around the entire training data with a batch of 64 and basically the epoch.
Okay. The next, so we made first epoch here, then we make the next epoch here, and when we make the next epoch, do we shuffle data somehow?
That's a very good question. Normally, or usually, no. Usually, no. But there is a parameter in Keras you can say shuffle data. But this shuffle data, I think it will work just initially. You will shuffle it initially, and then I think it doesn't really do it per epoch before each epoch. So it actually maybe it can happen that you may use the same batches all over again. It can happen. It can happen. I think from my perspective, I think it makes sense to shuffle because then you wouldn't really. I think it would improve the performance, but I'm not sure. I'm not sure that this is the way how the Keras implements the training loop. I think it shuffles only once before batches, and even for that one, you need to specify the parameter called shuffle equals true.
And with every epoch, we can drop out different neurons. Yeah. So this is actually the point. Yeah. That.
Moreover, actually, with the dropout, you drop random neurons for each image inside batch, not just for each batch, but for each image in the batch. Okay. Because when you use the batch, you don't really run it in parallel for the same network. You actually run them sequentially, and for each new image, you drop different neurons.
Mm-hmm.
And you can read all of that in this beautiful paper that I referenced. I think it's a very nice one. It actually explains that it does it for every data point, not for batch, not per batch. I was pretty sure that it does it per batch, but it wasn't doing it per batch.
And what's the guidance? How many epochs we need to run? Let's say not to use too many computation power on one head, plus to get more, let's say, generalized result.
It's a very good question, and that's why I have this plot curves function here. So the plot curves function, okay, that doesn't have accuracy. Why? What's wrong with you?
Just may I ask another question?
Yeah. Go ahead.
Okay, so we have in total 25,000 images, yeah? And we built a network. Then we are trying to feed the model, and we decided to choose 64 images for batch, yeah?
Yeah.
And we choose to use 20 epochs, okay? And we used only 5,000 images just to validate our model, yeah?
Yeah.
So,
so 10,000, I think it's, oh, no, you are right. It's 0.2, 20%. So it's 5,000 images, sorry.
Okay, so our validation split 5,000 pictures will be split by 64 pictures, yeah. So for as many batches as 5,000 divided by 64 equals, yeah. And
not really. I'm already not. I don't think so. I think in validation, in case of the validation, so epoch is only for training. What happens at the validation case is that you take all the validation images, you run them all through the network, and then you predict classes, and you're not doing the backpropagation. So batches are meant to backpropagate. So what happens in the batch, and this is what I would tell you if I would give you a lecture on deep learning, is that what happens in the batch is that you run these images. For each image in the batch, you calculate the error, you accumulate the error for the entire batch, and then you run backpropagation algorithm to correct the network. So when you're basically saying you are this wrong, correct yourself, and then the network goes back to the individual neurons, and it changes the weights in the neurons in such a way that this error would decrease. And then it does it in each batch, but it only works like this in the training case. When it does validation, it just takes all the images that there are in the validation set, runs it through the model with a feed-forward pass, and then it predicts class. And it predicts a class for each of the images and computes the accuracy, okay, and the error.
Okay, so
you can see it here.
Okay, so model uses all 5,000 pictures for each epoch, yeah?
Yeah.
And uses cumulative error of batch size just to make back propaganda to adjust weights in our
Please
model.
don't call it back propaganda. I really ask you for it. Please don't call it back. It's for all of you guys. Please don't refer to it back propagation. It hurts me right here.
Sorry, I will not.
Sorry for that. This is a side question. So go ahead. So you were saying we take all 5,000 images in validation set. We calculate the error and accuracy, and then this is just a monitoring. This is so-called babysitting, neural network training babysitting. Is when you see how your losses decrease and how your accuracy increases. Yeah. So you do it for validation, for the entire validation set. Sorry for my comment about backpropagation.
Oh, no, it's okay.
Couldn't help myself saying that. So
Dim, about back propagation, we run back propagation after every batch, or
every batch.
Okay, clear.
Every batch. Go ahead.
And what about number of steps? Do we specify somewhere number of steps? I mean, this 2000 divided on 64 or not? Because I remember in computer vision course, we did specify the number of steps because the algorithm couldn't stop itself.
I don't know. Maybe you were using some other model, but
okay.
Normally it is computed by default. You take the number of images, you divide by the number of batches, sorry, size of the batch, and you got your number of steps per epoch. This is number of steps. By the way, you can see that I got 20,000 steps, and I do 900 milliseconds per step. This is what the 900 milliseconds per step, or no, it's a milliseconds, microseconds. What is it? Is it the microseconds, guys? Do you know?
I don't know.
Microsecond. Anyway, it's been quite quick. So I have only 11 seconds per epoch. This is the entire time it took for the entire epoch. So having a batch size and then running through the entire training set, I had 20,000 images. So this is not number of steps, it's 20,000 images. And it doesn't really say how many steps I do per epoch, but you can calculate by dividing 20,000 by 64, and you will know how many steps I do. And you can, I think you can also, of course, you can also say, I want to have this many steps. And then the epoch would mean having this many steps times 64. Any other questions here?
Yeah, Dmitry, maybe you can explain what happened with weights during each epoch and after it, within each batch. Maybe just starting this, let's say there is no batches, just one big batch. And what happened with weights for each epoch? You start with random weights, and after it you get some optimal weights after the first epoch, and after it you start the second epoch with something, and you end up with something like that.
That somehow started getting here. Okay, so since Alexander was like, sorry, you can't see my slide. Sorry, I'll just share it. All right, so now you should see my slide. Since Alexander pointed out, I think it makes sense because it's basically like we are talking about something abstract and doesn't really exist in the universe. So let's really point it and let's nail it. So here's the data set. Let's imagine that this is our data set. It has only cats and dogs, right? Only cats and dogs. Two classes, cats and dogs. What happens is that we shuffle them. We just shuffle them. Then we call, some of them we call test set, and we hide it. Some of them we call validation set. And these ones we will keep for validation. What happens with the rest? We use the CNN, convolutional neural network, and we will use a batch size of 4. So for batch size, for each batch that we have in the data, and we will have batch size of 4, which means 4 images go into one batch. What we do, we calculate predictions from the network. So network predicts some scores for each class, right? We predict the class score for cat, and we predict class score for dog. Let's say we are talking about this specific image. This is image of a cat. We predict that, so the neural network predicted that this is a cat with 0.84. This is a dog with a 0.16, and the true class was cat. Ladies and gentlemen, do you guys see this? So this is a real cat. The score for a cat is 0.84. The score for a dog is 0.16. The true class is cat. Clear, right? This is a second image. We got the second score, 0.65 for cat, 0.35 for dog. It's true class is cat. Here we have a dog. But now you can see that what's the difference here is that we actually predict a higher score for a class cat than for a class dog, while the dog class is true class, right? And then we have the last image, which is a class of cat. Again, we make a mistake because the network predicted the score for class dog higher than the score for class cat, while the true class is cat. So this is what happens for batch. This is what happens per batch. when you have a batch, this is what neural network does, okay? Now what happens is that we calculate the error, right? How do we calculate the error? We calculate the binary cross entropy error. So this is what I have been telling you, and I said that I wouldn't explain it, but here I am explaining binary cross entropy. So binary cross entropy is having this horrific, absolutely unreadable formula, which I hate. But if you really look into it for more than a few seconds before you close the slides and go away home drinking beer, then you will actually understand it. Let me try to explain it. So this y here, y variable here, it basically is having only two possible values. It's 1 if a class is cat, and 0 if the true class is dog, right? So this is a true class, and it's 1 if it's a cat, and 0 if it's a dog, okay? Now, what is the P? The P is the probability of a class being cat, and this is what we predict, right? This is what we predict. This is our class score for cat. This is what the network is thinking, how much score it gives to the class cat for a specific image. And this is what is the score for a class dog, right? So this is 1 minus class cat. So what is the probability? What is the likelihood? What is how likely network thinks that this image belongs to a class dog? Okay, make sense, everybody?
Yep.
Igor?
Yep.
Does it make sense? You were like, I'm not sure which side you were nodding. You were like no or yes or somewhere in between. Okay, good. Now let's calculate it. All right. So what is the P for this first image? For the first image, what's P? Oleg, what is P for the first image?
0.84.
84, exactly. Y is 1 because it's a cat,
1,
right? Yeah, easy peasy. Now, what if we substitute these values inside a formula, right? So this is what we'll have. If you calculate this stuff, it's 0.25. So this is, I think, and we just take a logarithm and multiply. Here it's 0, so we don't care about this logarithm. We just take a logarithm 0.84. We multiply it by 1, and then we take a negative of that, and this is 0.25. This is 0.25. So this is error. This is an error of the first image. Simeon, why do you think we have an error? I mean, it doesn't seem to be a normal because, like, we have predicted a class cat, but it's still we still have some error. What's wrong with it? Why do we still have error?
Because the actual value is 1, and the prediction is 0.84.
Exactly. What would be so if to not have error, to have absolutely no error, this score has to be 1, right? But we were kind of close, but we weren't perfect, right? That's why we have some error. Okay. What happens to the other one? We calculate it the same way. We just substitute the values into the formula, and we got a value of 0.62. So you see how error grew. We were having 0.65 instead of 1, and the error grew from 25 to 0.62. Right? The score dropped for the true class, and the error has grown quite significantly. All right. So what happens about what happens in case we make an actual mistake? Right. So there is a class dog, but so the true class is dog, which means that y turns into 0. Here we go. This is y turns to 0. The P equals to 0.54. But again, this is a P of, this is the probability of this image being class cat, which is not the true class,
So
which means that sorry?
Yeah, so it knocks it out entirely.
Yeah. So we actually missed that part entirely, and the error is 1.12, which is a huge error, right? And we also calculated for the last image where the error is the largest, and we get 1.4. So this is what the total error looks like, okay? The total error is 3.39 for this batch, for the entire batch. We also calculate the average error. So we are not calculating just the sum of all errors, but we calculate the average error, which is 0.84. Now we do a backpropagation. meaning that we go into the network architecture and we change the weights so that the error would be the smallest. So we calculate these gradient with respect to all weights inside the network, and we change the weights in such a way that the error would be the smallest. So we shake a bit the network, and we say to the network, you know, you change yourself so that the next time I show you the same images, this error would be much smaller. And it basically is trying to do that. We also memorize this error, as in the error for the first batch. Then we take the second batch and we calculate all the same stuff. We get somewhat smaller error. We do back propagation. So we shake the network again. We record the error. We take the third batch. We calculate the error. We shake the network a little bit, and then we record the batch. Okay, the error for the batch. What happens now is that
sorry. When you shake network, there is no change in error.
There is no change in error because this has already been calculated. This stays as it is forever, but for the next time when we go through the same batch, this error will be smaller. So we change the network so that seeing the same images, we will have small error.
So but you get the network. So I mean, the changing of the weights is, okay, if you were going to do the first batch prediction again, what weights would result in a lower error? And it doesn't matter, as long as it's a little bit lower, then that's good enough. You stop there.
That's a very good question, and this is more about the part about backpropagation. So this is, you were saying, why do I need to know about backpropagation? So this is exactly what is the part of the backpropagation. There is also so the backpropagation is trying to minimize the error with respect to weights. So it changes weights so that the error is smallest. But there is a lot of our kind of mechanics of how exactly this is happening. You don't want to make a big step so that you overjump the minima. You also don't want to make too small step because this will just change it tiny little bit, non-significantly. So there is a whole chemistry behind how exactly you do the backpropagation. If we have time today, I'll happily go into this chemistry. I'll explain this chemistry. For now, let me just say that we do backpropagation, which tries to minimize the error with respect to weight. So it changes weight so that the error is getting smaller. But as you were saying,
by some amount.
So,
and whether that's bigger or smaller is where the magic comes.
Yeah.
So
it tries to approximately make a step so that it wouldn't do too much. So it wouldn't. But when you try to change the error too much, then you have a risk of actually doing worse, because you can actually make it very small for this batch of images, but you would actually overfit to these images, and the error would grow for the other images. So you don't want to make this kind of bigger steps. So you kind of try to make reasonable steps, and this reasonable is very important hyperparameter that you need to tune in cross-validation algorithm. So this is a very hard part of actual training of neural network, is knowing what is reasonable step for each backpropagation algorithm.
Thank you.
All right. So yeah, Oleg, did I answer your original question?
Yeah.
Okay. So we take the validation images now. Oh, sorry. We calculate the average for the training error. So this is our average training error. So if you when you will see in my code output of the average training error, this is what average training error per epoch looks like. This is how you calculate it. And then you take validation images, you calculate all the same stuff, and you call it a validation error. Okay, this is what validation error looks like. You calculate all the same things, and then you call it validation error, but you don't do backpropagation here. You just memorize it, okay? So what happens is that you do batch 1, batch 2, batch 3, and then you do validation, and this is one epoch. This is what one epoch looks like, okay? You do it, you collect the average training loss, you collect the validation loss, and then you do it for each epoch. Okay, and then you draw a graph. So this is a graph where you have average training loss and you have average validation loss, and they should be decreasing. And then you do more epochs, and then you see how they decrease. And basically, at some point, you can say, well, this gap here, it's an indicator of the overfitting. How is that as an indicator of the overfitting? Simon, why is that an overfitting here?
Because there is a huge difference in the metrics is increasing between the training set and validation set.
So there is a gap here, right? There is a gap here. As larger the gap, more overfitting is happening. Igor, doesn't make sense? Do you see what I mean by this?
Yep.
So you kind of learn to be good at the training examples, but you still kind of unsure about the validation performance, right? The validation performance is still kind of shaky, wakey, not so sure about. Okay. Does it make sense?
Yep.
Okay. So in this case, it's all good. The validation loss is decreasing with the training loss, and all is fine. So everything is okay. Both are decreasing in a very similar pace. So everything is okay. What happens? So this is training is normal. What happens here?
Noise.
Some weird stuff happening, right? So network has no idea what is she doing, right? What the network is doing. Sorry, I called network she, because in Russian we call it because it has a female gender, but it can be he or it, whatever. So the network doesn't know what the hell it is doing. And this usually means that you have some problem with the training data, and your training data doesn't really help, or it's too complicated. The task is too complicated. Maybe you have chosen a wrong loss function. Maybe you have chosen a wrong architecture. So the architecture is not strong enough to actually understand what's the problem. So you need to look into the architecture and see what the loss did you choose, what the architecture did you choose. Do you have enough data? Maybe it's you just have too much data, you have too little data. So these are the problems that can happen if you see this kind of image.
Would this be also back propagating that's making too big changes?
Yeah, this could be a too large learning rate. This is what the step size is called learning rate. So
Okay.
this could be a back propagation doing something. This could be the too large learning rate that starts to oscillate and that doesn't really converge to anything. That could be one of the reasons. This is a short discourse into back propagation. Actually, it's not about back propagation. It's just about very standard deep learning training pipeline. But I also have slides about specifically deep learning and back propagation part, which I still want to cover. I want to cover, I'm not sure if I want to cover it right now, maybe. Let's see, we have, okay, we still have some time. Let's try to cover some part of it. Okay, let's just try to cover some part of it. Let's consider a 2D example that has red points and purplish points, okay? We are looking at one specific point and one specific place here. We treat it as an input to our network. So the input of our network are the two coordinates of this point. So x coordinate and y coordinate, okay? Simple, easy peasy. Just the coordinates are the inputs. So these are the input neurons. We have this simplistic structure where we have a hidden layer and we have the output layer. We also have weights that connect these layers, and these weights have certain values. Let's say W1 is equal to 0.15, W2 is equal to 0.20, and W2 is connecting X with this hidden layer, with this hidden neuron number 1. We have true values. So we know that the point is reddish. So the score of the reddish class should be 1. The score on the purplish class should be 0. That is the target. That's what we want to get, okay? We also have biases. This is something that you may not have heard about, so I explain it separately. But since I didn't explain the sigmoidal function, that's going to be a bit harder. Since I'm just jumping around my lecture, I actually, my lecture is is more of from the start till the end. So I did explain the sigmoidal before, but just let's try to understand it together. So normal layer without biases have this input, some value, then it has a weight, and then it has a neuron. A neuron is basically just taking a product of W1 times X and passes it through this function that is called sigmoidal function, right? The sigmoidal function. And the sigmoidal function looks like this. When we change the W, when we make W smaller or bigger, the sigmoid starts to look different. So it starts to look more like this. So it's basically either it's gets squished, squashed, or it get expanded. When we add a bias inside the function, we have sigmoidal function that is fed on top of W1 times X plus B1. So this is what happens. This is what happens when you add the bias into the picture. Okay. Why do we need bias? Because bias adds additional flexibility. By adding some bias, we move the sigmoidal function along the x-axis here, and we get a bigger power. We have more power. We can get more interesting performance of our of this neuron by adding bias. So we can actually shift the values along x-axis. Okay. Have you guys heard about sigmoidal function?
Yeah, sure.
Yes.
What is the formula for the sigmoidal function? Okay.
Some logarithmic, some.
No, it's not logarithmic. It's e to the power.
E to the power of, yeah.
But it's not just e to the power. It's also, there is a ratio. So it's something divided by something plus e to the power. So it's a bit complicated formula, but it just results in this very nice wave-looking shape. So if you would fit in x from -8 to 8, and you would just fit into this function, this would be the y values that you would come up with. This would be the y values. This would be the output.
We see it as activation function, for example.
Sorry?
Yeah, activation function.
This is an activation function. Yeah, this is one of the types of the activation functions. Yeah, this is the formula for a sigmoidal function, just in case. So it's 1 over 1 plus e to the power minus x. Okay. And this is a formula for a sigmoidal function with bias, right? So you have wx plus b. So this plus b is this bias term, right? If you wouldn't have the bias term, you would have just wx. Okay. So this is what happens inside the neuron, and this is what happens in the biases. Now the challenge here is to calculate the outputs, the answers, these question marks here, of what the what the network has to say about this point. Which class does it predict? So that is the key question of this part of the lecture. And let's see how we do a feed-forward pass. So this is a feed-forward pass. There are two major algorithms involved in neural network. One is called feed-forward pass. The other one is called backpropagation algorithm. Okay, this is a feed-forward path. Now let's calculate the input of this neuron. Kenneth, can you help me? What should I do? What is the input of this neuron?
The weights by the multiplied by the
input.
The input,
right?
Yeah.
Yeah. So Igor, can you tell me, so no calculation, just with words, how do I calculate the input of this neuron? Just tell me what value times what value plus what value times what value plus what value.
I think 0.05 multiplied by 0.15, then 0.1 multiplied by 0.20, then what is B?
Bias. So what is this? You were all good. This is all good. But what does this then word in your, so in your sentence you used then? Sorry?
I think plus.
Plus, exactly. So you're saying 0.05 times 0.15 plus 0.1 times 0.2 plus 0.35, right? So this is what comes in on the input of the hidden neuron number 1. All right, and I just calculated it 0.3775. Okay, 3775 doesn't matter. Now, what is the output of this neuron? What is the output of this neuron? This is a sigmoidal function, right? So we take a sigmoidal function, which was, Olena, what's the sigmoidal function again? You were saying?
1 divided 1 plus...
what was that?
E powered minus x.
Exactly, right? So basically what I do is that I just take x value, which is 0.3775, and I project it onto this line, which is a sigmoidal function, and I grab the y value as a result of this. Simon, what's the result of this?
I think it's 0.59.
Yeah, something like 5933. Exactly. You were super close. You were super close, like 0.03 error. Yeah, that's the output of this neuron. Pretty good. Now we can calculate the input of the second neuron. Oleg, can you just with words tell me what should I calculate?
Second neuron.
Yeah, this one. Here we go. This one.
0.05 multiplied by 0.25.
Yeah.
Plus 0.1 multiplied by 0.33 plus 0.35.
Excellent. It's excellent. So this is what it is. It's 0.3925. 0.3925. If we use the sigmoidal function, then it gives us a 0.5969. Okay, this is the output of this neuron. All right, so we have an input. We need to pass it through the sigmoidal activation function, and this is the value that we get. Do you guys have questions so far?
Did we use bias for sigmoid function in this case?
So the bias goes inside here. Bias is part of this input, right? So if we look at the slides where I explained about the thing about bias.
Yeah.
So
I mean this one, yeah.
So we use bias right here. So we add it to the value that goes inside into the sigmoidal function. So we multiply W times X and we add the bias, and then we use sigmoidal function on top of that. That's what we did, right?
Okay.
Beautiful. Do you guys have other questions about this? Igor? They're all good? Make sense? Lena? No? No good?
Good.
Oh, good. Oh, good. All right. So of course we need to continue the same stuff for the for this neuron. We need to calculate all the same things again. It's just now the instead of using the 0.5 and 0.1, 0.05, sorry, and 0.1, we use the outputs of these neurons, right?
Yep. Output times weight plus output times weight plus bias.
Plus the second bias, right? Plus the another bias. And it's all the same mechanics. It's all over again. It's the same stuff. Then we use again the sigmoidal function, and we get the output of this neuron, right? And then we calculate it for the second neuron, all the same stuff. We just use the outputs of these neurons as inputs, right, to these weights. And then we just calculate the outputs of these neurons. So these outputs are what we consider to be class scores. Class scores, okay? Simeon, should we be happy about these class scores? Should we be happy about these class scores?
Not sure.
Not sure. What does it what does make you feel not comfortable about these scores?
The difference is the difference looks small.
The difference looks small here, right?
Mm-hmm. Mm-hmm.
But what about this difference? Does it look as small?
No, not small. Of course, not small. But it is. We come from the x and y at the beginning, from real values. After that, we put it to sigmoid function twice.
Yeah.
So at the end, what we have? Should we find a way to somehow to put back from the sigmoid to normal figures? No.
No, it's this is just an input, and the network should find a way to map these inputs into these labels. So here it should be as close to 0 as possible, and here it should be as close to 1 as possible.
So then the result is good.
Is it? Oleg, are you happy with the result?
See,
Sorry, I would expect that this 751 shall be closer to 0, yeah, to have it good.
Yeah. Kenneth, you were saying.
Yeah. My understanding is that both of these are predicting towards the truth value, but one is predicting toward. So we know it's red. So shouldn't both of these answers be getting closer to red, to 1.0?
So this is a score of the first of the class purple. This is how much our network thinks that this point here is a purple point. And this is a score that says how much our network thinks that this is a red point.
Oh, so it calculates those percentages entirely independently. It's not doing one minus of the two. Okay.
Yeah. So they are independent. They are not probabilities. They are not supposed to sum up to 1. Okay.
Okay.
So they are independent, and this one should be as close to 0 as possible, and this one should be as close to 1 as possible. So what happens is that we try to quantify our kind of feeling about these answers by calculating the error, right? And in this very specific case, I know that I just showed you BCE, binary cross entropy, but in this very specific case, I calculate MSE, mean squared error, just because in here it looks more of a regression problem, but it doesn't matter. We could have used BCE in here as well, okay? But in this very specific case, just for the sake of example, I use MSC, which is truth, which is 0, minus the output squared divided by 2. And I'll explain why divided by 2, because we have 2 neurons. If we multiply it, we get a 0.282. This is the error of on the first neuron, okay? On the first class. This is an error on the first class. I can calculate the same error for the second class, and I get way smaller value, 0.025, okay? So these are the 2 errors that I have. Does this make sense, ladies and gentlemen? Does this all make sense? So I just calculated the error for the first class, I calculated the error for the second class, and these are the values that I end up having. Igor, does it make sense?
Hope so.
Ask me, please. Tell me whatever doesn't make sense. What confuses you? Please tell me. I'll be happy to go back and rewind some stuff.
I would expect big error for purple.
Yeah, the BCE would give bigger error, but
I think we should find a way to convert it from sigmoid function to just to real figures, to coordinates. So 0.28 from sigmoid function means a much higher figure. No?
Simon, what do you mean by real figures? What do you mean?
I mean, we received the like logarithm. You know, when you receive result as a logarithm, you should then calculate it back to the value.
No, but we treat them as class scores. It doesn't really matter. I mean, what are these? What are the specific functions that we have here? We treat them as class scores. We try to learn a network that would be a mapping from the coordinates into the class scores. They shouldn't be coordinates here.
Yeah, it's because
these are not coordinates.
Because we're going the value is just between 0 and 1, right?
Yeah.
We do want to stay the log.
Okay, yeah, I understood now.
Yeah. Igor, do you have an idea what confuses you? What's the confusing part here?
That's interesting. Well, just I don't know. I'm trying to think broadly. I don't like this answer.
Yeah, I don't like it either. I think nobody should like this answer. I think it's fairly not good answer. But do you understand the flow, the idea, the main idea? We take the coordinates of the point, we put it through some mathematical operations. Doesn't really matter what kind of mathematical operations. This mathematical operations result in two numbers, just two numbers. One we treat as a score for the first class. The other one we treat as a class for the score for the second class, and then we calculate the error of these mathematical operations. That's all there is.
So, but basically, what we're saying is that this is terrible at its job before any backpropagation happens.
Exactly, it is terrible at its job. That's what we are saying here. That is what we are saying here. It wasn't really terrible here. It was kind of fine, but it was extremely bad on this side. Okay.
Yeah, which means that it's likely terrible in both ways. It's lucky.
Yeah.
Ones.
Yeah. Okay, gotcha. That makes sense. Lena, does this make sense?
Yes.
Yes. Are you sure? So what is it that doesn't make sense? Let me know what doesn't make sense. I know I shut up.
Yeah.
You say.
It's okay. Is it maybe we need to change weight or?
Yeah, we should. I'm getting there. I'm getting there. Just this is initial feed-forward pass. This is, ladies and gentlemen, this was just an example. What happens when you take a randomly initialized network? You take the first point, and this is what happens to the first point, right? We get a vastly bad predictions. Okay, not very good answers.
These were all random weights. The first sets of weights are fully random.
Yeah.
Excuse me.
Random weights.
Excuse me, but it means that we calculated the error correctly.
Yeah, we calculated the error correctly.
But why it does not look dangerous? Millions of something, just 0.20.
Oh, but that's, yeah, you know, depends on the error value. You could have calculated something else, but this is pretty bad actually. This is already pretty bad.
Yeah, I understand.
You don't need millions to understand that there is something wrong happening here. You know what? Let's make a break for 10 minutes and let's come back to the backpropagation part. Okay? See you all at 12. Okay? See you all at 12.